Hello, my dear Butcho, and welcome back. I know. Exams are right around the corner and the pressure is really building up. And this chapter, equilibrium, it can sometimes feel a little wobbly, can it? Kind of like you're trying to balance on one foot. But hey, don't you worry one bit. Because today, we're going to make this chapter super simple. Seriously, think of it less like a tough chemistry topic and more like a secret code. And in the next few minutes, you and we're going to crack this code together. Ready? Chalo, let's go. Okay, so here's our game plan. First, we'll figure out what dynamic equilibrium actually is. Then we'll see how this balance works for physical states and for chemical reactions. After that, we meet the magic number, Kc. And finally, we'll learn how to predict which way a reaction will go. It's a simple roadmap to get you full marks. Right, first things first. What on earth is this equilibrium thing everyone talks about? Well, the most important word you need to remember is dynamic. This means it's not about things coming to a dead stop. Oh no, it's a secret balancing act that's happening all the time, everywhere. So here's the main idea. Listen carefully. Dynamic equilibrium is that special moment when the speed of the forward reaction, reactants becoming products, becomes exactly the same as the speed of the reverse reaction, where products are turning back into reactants. So from the outside, it looks like nothing is happening. But inside, it's total action. Molecules are going back and forth at the exact same pace.
To make this crystal clear, just imagine your favorite Pani Puri wala at a mela. He's making those delicious puris and putting them on the counter, right? And you and your friends are buying them just as fast. Now, if he makes, say, 10 puris every minute, and you guys eat 10 puris every minute, tell me, will the number of puris on his counter change? No, it will look the same. That, my dear students, is dynamic equilibrium. Things are happening, but the overall amount stays constant.
Okay, next stop on our roadmap. This amazing balancing act doesn't just happen in those chemical equations. It also happens when things change state. Like when solid ice melts into liquid water, or when that water evaporates into steam. And for your exams, you just need to focus on these three types. First, between a solid and a liquid. Think of ice and water in a glass at exactly 0 degrees Celsius. Then, between a liquid and a gas, like water and water vapor in a sealed bottle. And finally, between a solid and a gas. You've seen this with camphor, right? How it just disappears? That's sublimation. It's the same idea of balance in all three cases. Now, listen up, because this is a super important point. A rule you can never forget. For this balance to happen, this system must be closed. Think about it. If you leave a glass of water open on your table, the water level will go down, right? The vapor just escapes. There's no equilibrium. You need a lid on the pot, a cap on the bottle, so that the molecules that escape as gas can also get trapped and turn back into liquid. All right, time for the main event, chemical equilibrium itself. The best way to picture this is like a game of tug-of-war. On one side of the rope, you have the reactants, pulling hard to become products. And on the other side, you have the products, pulling to change back into reactants. And this graph from your textbook shows it perfectly. Look here. At the start, you have lots of reactants, so their concentration goes down. You have 0 products, so their concentration starts going up. But then, see this part where the lines become flat? That's it. That's the moment their concentrations stop changing. That's equilibrium. The tug-of-war is a perfect tie. And here is a mind-blowing fact. A favorite for exam questions, by the way. It doesn't matter which side you start the reaction from. You can start with a flask full of only reactants, or, get this, a flask full of only products. As long as the conditions are the same, you will end up with the exact same balanced mixture. How cool is that? So, you're probably thinking, okay, this balance point is special, but is there a way to, measure it with a number? Yes, there is. And that's where our hero comes in, the equilibrium constant, Kc. Just think of Kc as a magic number that tells us everything about the reaction's balance. Now, I know this formula looks a bit scary, but trust me, it's so simple. All it's saying is that Kc is a fraction. On the top, you put the concentration of the products. On the bottom, you put the concentration of the reactants. And those little balancing numbers from the equation, they just become the powers. That's it. Always remember, products over reactants. Let's make this foolproof with 4 simple steps. Step 1, just draw a line for the fraction. Step 2, put the products on top. Step 3, put the reactants at the bottom. And step 4, the final touch, make those balancing numbers the powers for each one. See? Easy peasy. You'll never get it wrong again.
Okay, enough theory. Let's practice. Here is a question straight from your NCERT textbook. This is exactly the type of problem you'll see in your exam. They give you the balanced equation, they give you the concentrations at equilibrium, and they ask you to find that magic number, Kc.
So we just follow our steps. First, let's write the expression. Products on top, so that's ammonia, NH3. The balancing number is 2, so it's NH3 squared. Reactants at the bottom, that's N2 and H2. The number for H2 is 3, so it becomes H2 cubed. Now, we just put in the numbers they gave us. Just be very, very careful with those powers when you calculate. And once you punch that into your calculator, voila! You get the answer 3.55 into 10 to the power of 2. See? Not so bad, right? Once you know the formula and the steps, these problems are actually quite simple. Great job! So we can find the value of Kc. But so what? What does this number actually tell us? Well, this is the really cool part. This number is like a crystal ball. It lets us predict the future of a reaction. We can become chemical fortune tellers. Take a look at this seesaw. Remember, Kc is products divided by reactants. So if Kc is a really, really tiny number, what does that mean? It means the number on the bottom, the reactants, must be huge. And the number on top, the products, is tiny. The seesaw is tilted all the way to the reactant side. The reaction has barely even started. In this tug-of-war, the reactants win. Now look at the opposite. What if Kc is a massive number? Well, that means the number on top, the products, must be huge, and the reactants at the bottom are tiny. The seesaw is tilted all the way to the products side. The reaction is almost completely finished. This time, the products totally win the tug-of-war. Okay, one last detective tool. What if a reaction is happening, but we don't know if it's at its balance point yet? For that, we use something called the reaction quotient, QC. It's calculated exactly like Kc, but it's like a snapshot of the reaction right now. Then we just compare our snapshot, QC, with the final destination, Kc. If QC is smaller than Kc, the reaction needs to make more products, so it moves forward. If QC is bigger than Kc, it's gone too far. It needs to go in reverse. And if QC equals Kc, perfect, you're already at equilibrium. So let's wrap this all up. Here are your 5 exam superpowers for this chapter. 1. Equilibrium is dynamic, not static. 2. It only happens in closed systems. 3. Kc is always products over reactants. 4. A big Kc means lots of products. And 5. A small Kc means mostly reactants. If you remember these 5 points, you are all set for this chapter. See, bachcho, equilibrium isn't a scary topic. It's all about finding a perfect, dynamic balance. And that's what I wish for all of you right now, to find that perfect balance between studying hard for your exams and also taking time to relax and have fun. You can do this. I have full faith in you. I really hope this has helped you find your balance with equilibrium. Now, I want to hear from you. Tell me in the comments, which chapter is giving you trouble? Which topic should we crack the code for next? Let me know and we will make it simple together. All the very best for your exams.